In this video, we're going to explore an example of a basis of a vector space. The vector space that we're going to look at will be the vector space of polynomials of degree 1. So the notation for a space like this would be P1, and the vectors in this space are all formal expressions of the form ax plus b, where a and b can be arbitrary real numbers. We are looking at polynomials with coefficients being real numbers. So in this vector space, the vectors are polynomials, and of course a polynomial is determined by the two coefficients, the a and the b. The x there is just a formal symbol. We're not necessarily thinking of polynomials as functions, although they could be thought of as functions. And what we want to do now is to point out one particular basis for this vector space. In general, vector spaces have multiple bases, and the obvious one for this space would be the one where we have two vectors in the basis, v1 equals to 1, and the second vector is v2 equals to x. This is a basis because what makes a basis in general is that you've got a certain sequence of linearly independent vectors, and any vector in your space can be expressed as a linear combination of those vectors, and that's what the basis is. And so these two vectors are linearly independent, and any vector in this space can be expressed as a linear combination of these two, because ax plus b can be written out as a times x plus b times 1, in other words, as a times v2 plus b times v1. And in fact, this is the unique way of writing down a given vector as a linear combination of these two specific ones, of the v2 and the v1. And in general, that's the feature of a basis, that when you've got a vector expressed as a linear combination, the expression will always be unique in the coefficients. There will always be unique sequence of coefficients allowing the expression. This was an easy basis in the sense that it's easy to figure out. Given the form of the vectors that we have, it's easy to figure out how to express a vector as a linear combination of the basis vectors. But there could be other bases which would force us to engage into certain computations before we can find the expression of a vector as a linear combination of the basis vectors. And in particular, the basis we're going to be looking at in this video consist of the following two vectors. One is x plus 1, the polynomial x plus 1, and the other one is the polynomial x minus 1. This is another basis of the same space, and no wonder that the number of vectors in this basis is the same as in the other one, which is 2. This has to do with the fact that the space has dimension 2. In general, any two bases will always have the same amount of vectors in them. So the space of first order polynomials being a space having dimension 2 guarantees that the basis in this space, any basis, will have exactly two vectors in it. And so this second sequence of vectors is a basis having two vectors in it because of the dimension being 2. And what we want is to illustrate how we would be able to find a basis for how we would be able to find a linear combination in terms of this basis of some random vector. And for the example's sake, let's take the polynomial p of x equals 5x plus 2. So the question is, how can we express 5x plus 2 as a linear combination of the two basis vectors b1 and b2 given above. So we want to find C1 and C2, which makes this equality hold. As we said in the other case, it was kind of easy because of the form that the polynomial has. In this case, it will be a bit more difficult because now we are looking for C1 and C2, which makes the equality hold. And the equality is, on the left-hand side, we have the vector in question, and on the right-hand side, we have C1 times x plus 1 plus C2 times x minus 1. And of course, this expands to C1 plus C2 times x. So now we are doing the calculation to work out what the right-hand side polynomial is. And so we get C1 plus C2x by rearranging the terms and opening up the brackets and then closing them again in a different way, plus C1 minus C2 times 1. And so, because we want this polynomial to be the same polynomial as this one, we would want the coefficients of the polynomials to match as well. That's what makes two polynomials equal, if they have the same coefficients. So 5 should match with C1 plus C2, and 2 should match with C1 minus C2. And writing this down, what we get is, of course, a system of linear equations. So C1 plus C2 needs to be equal to 5, and C1 minus C2 needs to be equal to 2. And any C1, C2 that makes this these pair of equalities hold will have the vector 5x plus 2 expressed as a linear combination of the b1 and the b2 vectors from the basis, with C1 and C2 serving as the coefficients in the linear combination. Basically, to solve the problem, we need to solve a system of linear equations. And so, it's not a very difficult system to solve, of course. So let's carry this system down to the next slide. And so what we've got in the next slide is the following. It's not even worth writing down the matrix for it. We can directly solve this, or maybe we can do it even in a better way. The sum of the two rows gives us 2C1, because C2's cancel, so that's going to be equal to 7. So C1 is equal to 7 divided by 2, and that makes C2 equal 5 minus 7 divided by 2, and of course 5 is 10 divided by 2, so 10 divided by 7 minus 7 divided by 2 is going to be 3 divided by 2. And if we want to double check the answer, we need to get that C1 plus C2 is equal to 5, and indeed it is, because 7 over 2 plus 3 over 2 is equal to 10 over 2, which is 5. And we also want to check that C1 minus C2 is equal to 2, which it is, because 7 over 2 minus 3 over 2 is going to be 4 over 2, which is equal to 2. Great. So we figured out that the polynomial that we had, which was 5x plus 2, can be expressed as a linear combination of b1 and b2, with the coefficients being 7 over 2, so 7 over 2 times b1, plus 3 over 2 times b2. So here is an example demonstrating how we could find coefficients expressing a vector in terms of the basis vectors. But how do we know that we would be able to find these coefficients? Well, we know this by the fact that the given sequence of vectors was a basis. But how can we establish that it was a basis? So let's go a bit beyond what we originally planned to do. Originally, we just wanted to get an expression of 5x plus 2 as a linear combination. But now, in addition to that, let us try to think, if we had been given the task of establishing that this sequence of vectors is a basis, what would have we needed to do for that? There is a longer way and a shorter way. The longer way would have required us to check two things. First of all, that the sequence b1, b2 is linearly independent, because this is part of the requirements of being a basis. And secondly, that the span of this set is the entire space, which in our case is P1. Let me focus on the second one for a little bit. So what does this mean? This means that any vector in the space is expressible as a linear combination of b1 and b2. We just found that 5x plus 2 is. And with a similar method, with exactly the same method of solving a linear system, we can establish, we would have been able to establish that any other vector we pick, and we would have then worked with a general vector ax plus b. And for that a and b, which now would have been general variables, we would have worked out if we can get the c1 and c2. And if we can always do that, then this would have allowed us to say that the span of b1 and b2 is indeed p1, because the span is the set of all linear combinations. And so if all linear combinations reach all of this space, then they are the same. Remember, maybe I should actually be a bit more precise in here. So we have here equality of two sets. So for this equality to hold, we want one set to be inside the other and the other way around, right? So we want these to be parts of each other. Now the thing is that span of b1, b2 is automatically inside p1, because b1 and b2 come from the space p1, so their arbitrary linear combinations will also fall in the space. So we automatically have that this is inside here. So in order for us to check that they're equal, we also want to establish that p1 is inside span b1, b2. And to establish that, we would pick any vector in here and check if it's in the other one. And being in the other one means being a linear combination. Like for 5x plus 2, since it's a linear combination of b1 and b2, we can then say that 5x plus 2 belongs to the span of b1 and b2, because the span of b1 and b2 is the set of all possible linear combinations. It can be written down like this: is the set of all c1 b1 plus c2 b2s, where c1 and c2 can be any real number. Okay, so knowing that 5x plus 2 is in the span, it's fine. But now if we can know that any vector is still in the span, and we could have worked this out by checking, by solving the system for a general a and b instead of 5 and a 2, to establish this equality. What about for linear independence? What would it take to establish that the b1 and the b2 are linearly independent? Well, we would have to apply the definition of linear independence, but we could also do something a bit quicker, and namely to verify that none of these is a linear combination of the other. Can x plus 1 be written as some constant times x minus 1? No. And also the other way around, the answer is no. In fact, only one way around is already enough, knowing that these are non-zero vectors. So more or less, that's how we could have checked that the b1 and b2 are linearly independent. We're going to go into the actual checking of it in a moment. And so in the end, once I check that the two vectors are linearly independent and they span the entire space, then I can say that these two vectors form a basis for the space. This is by the definition of a basis. It needs to span the entire space and it needs to be linearly independent. The shortcut that I was referring to earlier that we could take is the following. We could make use of the fact that we know that P1 has dimension 2. And when a vector space has dimension 2, it is sufficient just to check one of these two instead of both. So if there are, in other words, if there are two vectors in a two-dimensional space that are linearly independent, necessarily those two vectors will form a basis. So the other condition will automatically hold. And also the other way around, if I have two vectors in a two-dimensional space that span the entire space, necessarily those two vectors will be linearly independent and therefore it will be a basis. So knowing that P1 has dimension 2, we could shortcut checking for basis by checking only one of these two requirements. And the one we're going to do now in this video is the first one. So let's see how we could establish that the vectors B1 and B2 are linearly independent. So what we want to do is to prove that B1 being equal to x plus 1 and B2 being equal to x minus 1, that these two vectors are linearly independent. Now there are multiple ways to do that as well, depending on which formulation of linear independence we use. One very useful way of determining whether something is linearly independent is the following way. Imagine we have not just two, but maybe several vectors. So this method for checking for linear independence states that all you need to do is check that the first vector isn't the zero vector. When the zero vector is in a sequence, that sequence is automatically linearly dependent, okay? So we don't want B1 to be zero vector. Once we check that, what we need to do is to check that B2 isn't a linear combination of the previous vectors, but there is only one previous vector, so we need to check that B2 isn't equal to some C1 times B1. And then for the third one, we have to check, so once that, if it is equal to, that's it, the sequence is linearly dependent. But if it isn't, then for the third one, we want to check the third vector isn't a linear combination of the previous two. So we want, maybe I'm going to expand this a little bit, including a few other terms here to demonstrate the pattern of what are we doing at each step. So we don't want B2 to be equal to C1 times B1 plus C2 times B2. For no values of C1 and C2, we want this to be true. And then we go on like this. So at each step, we will be checking that that vector in that step isn't a linear combination of all the preceding vectors. And at the end, once we arrive at the last vector, we will do that exactly the same thing for the last vector. So we want to check that the last vector isn't a linear combination of the previous ones, in which case we are saying that Bn isn't a linear combination of the vectors B1 up to Bn minus 1. Now, in our case, when we have only two vectors, we just need to do two things. So in our case, the scheme here reduces to this scheme. And so what we need to check is that x plus 1 isn't the zero vector. And of course it isn't, because the zero vector in the space of polynomials is the zero polynomial, and x plus 1 is certainly not the zero polynomial. And then the second thing we need to check is that B2 isn't a linear combination of B1. So we need to check that there is no way that x minus 1 is equal to k times x plus, well, I shouldn't use k maybe because I've already called this C1 there. So let's call it C1. That x minus 1 isn't equal to C1 times x plus 1. Well, C1 times x plus 1 is C1x plus C1. And we want not to be able to find a C1 for which this equality holds. Okay, so let's see. What does it take to do that? Okay, so typically in mathematics, when you want to prove that something doesn't work, the common strategy there is to see what if it did work and see what result you get out of that. And very often what happens is that you are able to show that if it did work, then something ridiculous should have happened, and you know this ridiculous thing cannot happen, so the thing cannot work as a conclusion. So if x minus 1 was equal, let's say x minus 1 was equal to c1x plus c1, then what should have happened is that c1 must have been equal to 1, because that's the coefficient of the polynomial that should match with the coefficient here. There is an invisible coefficient here of 1, right? By the equality of polynomials, by the way, right? Two polynomials are equal if their coefficients are equal. So c1 must equal to 1, but at the same time, the other coefficient should be equal to the other coefficient here. And the other coefficient here is not 1, but it's minus 1. So this is minus 1 times 1 that we have here, right? The official expression of x minus 1 polynomial is 1 times x plus minus 1 times 1. And so the same c1 then has to be equal to minus 1. So the only way that b2 can be c times b1 in this case is if there is a number c1 that is equal to 1 and minus 1 at the same time. And of course there isn't such a number. So that shows that x minus 1 cannot be equal to c times x plus 1. Of course, we could have also argued in a more traditional way, these two things being equal is the following system having a solution, the system of c1 being equal to 1 and the same c1 being equal to minus 1, and then we say, okay, the system does not have a solution, therefore there isn't such a c1 that makes b2 equal to c1 times b1. Great. So what we've established now is that according to this algorithm, we've established that, well, according to the algorithm says that if you do these checkings all the way from b1 up to bn, and then in the end you end up at neither place having equality, then you can be sure that the sequence is linearly independent. And so we carried out the algorithm and we got the positive result that never ever did we get the equality. Maybe we shouldn't call it a positive result, but it is positive in the sense that the algorithm now confirms that this sequence is linearly independent. Now the difference between the algorithm and the actual definition of linear independence would have been that if I had to apply the definition directly, then I would have had to make sure that whenever this holds, I get from this that c1 equals c2 and equals 0. And this is not difficult to do. The algorithm is simpler in the sense that to do this implication, we would have to work with a system of equations with two variables, c1 and c2, and in the algorithm, the number of variables has been reduced by 1. Of course, in the case of two terms, this is not such a significant simplification, but you can imagine when you have many functions here, it might be that the algorithm can get us to check things a bit quicker than directly by applying the definition of linear independence. Well, at least the algorithm is certainly useful in detecting when something is linearly dependent, but also for systematically checking for linear independence. Sometimes it is easier to see, thinking in terms of linear combinations, in terms of one thing being a linear combination of the other. It is easier to see whether the sequence is linearly independent or not than to go through the default way of directly applying the definition for linear independence. But of course, the methods are all equivalent to each other, so either way you take, you will always get the same answer. Thank you for watching the video. Before concluding the video, I would like to summarize what we did. So let's go a few slides back. So we had here a space of polynomials of degree 1 at most. And in this space we had a very strange basis consisting of two vectors, x plus 1 and x minus 1. Knowing that it's a basis in a two-dimensional space, we know any vector can be expressed as a linear combination of these two, and as an illustration of this we've expressed 5x plus 2 as a linear combination. And once we did that, then we embarked on a more ambitious goal to actually prove that these two vectors do form a basis. And we remarked that to do that, since we know the dimension, the space is dimension 2, it is sufficient just to prove one of the requirements of a basis. There are two requirements: linear independence and spanning the entire space. And so since the dimension is 2, it is, and we have two vectors at hand. By the way, if we didn't have two vectors and the dimension was 2, we can be sure that the sequence is not a basis. Okay, so the number of vectors in the sequence matched with the dimension, and therefore it is sufficient just to check one of the two, either linear independence or the spanning condition. And we checked for linear independence for B1 and B2, and we saw that the sequence is indeed linear independent. And to do that, we applied a special algorithm for checking for linear independence. Thank you.